Good morning, everyone. I am Zairine Castillo, BS Mechanical Engineering 321, and today I'm going to present to you Chapter 6 entitled Mechanical Properties of Metals, Part 2. True stress and strain. True stress is defined as the instantaneous applied load divided by the instantaneous cross-sectional area. However, true strain is equal to the natural logarithm of the ratio of instantaneous and original specimen lengths. The formula for true stress and strain are: true stress is equals to load F over instantaneous cross-sectional area A, and true strain is equals to the natural logarithm of instantaneous length over original length. So, if no volume change occurs during the deformation, this is the formula. Instantaneous area multiplied by instantaneous length is equals to original area multiplied by original length. However, true and engineering stress and strain are related according to these formulas. True stress is equals to stress multiplied by the quantity of 1 plus strain. And true strain is equals to the natural logarithm multiplied by the quantity of 1 plus strain. So, take a look at this example problem. A cylindrical specimen of steel having an original diameter of 12.8 millimeters or 0.505 inches is tensile tested to fracture and found to have an engineering fracture strength of 460 megapascal. If its cross-sectional diameter at fracture is 10.7 millimeters, determine the ductility in terms of percentage reduction in area and true stress at fracture. So, to find the ductility in terms of percentage of the reduction area, we will use the formula percentage of the reduction in area is equals to the quantity of original area minus fracture area over original area multiplied by 100. So, for us to find the ductility in terms of percentage reduction area, we will have to use 12.8 millimeters over 2 squared times pi minus the quantity of 10.7 millimeters over 2 squared pi over the quantity of 12.8 millimeters over 2 squared pi multiplied by 100. So, i-input natin to sa calcu and we will get 30%. So, the ductility in terms of percentage reduction area of this problem is equals to 30%. So, to find the true stress at fracture, we will have to find first the fracture. So, F is equals to true stress multiplied by original area. If we input this na calcu, we will find 59.200 Newton. So, yun yung gagamitin natin bilang F sa ating original formula, which is true stress is equals to load F over fracture area is equals to 59,200 Newton over the quantity of 89.9 millimeters squared multiplied by 1 meter squared over 10 raised to 6 millimeters squared. We will get the answer. True stress is equals to 6.6 times 10 raised to 8 Newton per meter squared or 660 megapascal or 95,700 psi. Elastic recovery after plastic deformation refers to the temporary shape change that is self-reversing after the force is removed, so that the object returns to its original shape. It is called elastic deformation. When the stress is sufficient to permanently deform the metal, it is called plastic deformation. So, upon the release of the load during the course of a stress-strain test, some fraction of the total deformation is recovered as elastic strain. So, compressive, shear, and torsional deformations. Metal may experience plastic deformation under the influence of applied compressive, shear, and torsional loads. The resulting stress-strain behavior to the plastic region is similar to the tensile counterpart. So, ibig sabihin, ang tumutukoy sa plastic deformation ay permanently na madedeform yung metal na gagamit ng compressive, shear, at torsional loads. So, another mechanical property that may be important to consider is hardness, which is a measure of material's resistance to localized plastic deformation, for example, a small dent or scratch. So, mahalaga sa metal, sa mechanical property ng metal na malaman natin ang hardness nito or masukat natin ang hardness nito. Kung sila ba ay nakaka-resist sila ng mga heavy loads para hindi agad sila ma-deform, or kung hindi agad sila nagkakaroon ng small dent or scratch. Mahalagang matukoy yon sa metal. Hardness tests are performed more frequently than any other mechanical test for several reasons. First, they are simple and inexpensive. So typically, no special specimen need to be prepared, and the other testing apparatus is relatively inexpensive. Ibig sabihin, mas mura kumpara sa ibang mechanical test ang pagtetest ng hardness ng isang metal. Number 2, the test is non-destructive. So, the specimen is neither fractured nor excessively deformed. A small indentation is only deformation. And number 3, other mechanical properties often may be estimated from hardness data such as tensile strength. The depth or size of the resulting indentation is measured and related to hardness number. So, the softer the material, the larger and deeper the indentation, and the lower the hardness of the index number. So, yun nga, hardness is measured by material resistance to localized plastic deformation. So, there are two most common hardness testing techniques, such as Rockwell and Brinell test. So, Brinell test is there is a single scale. Brinell hardness is determined from indentation size. However, Rockwell test is based on the difference in indentation depth from the imposition of minor and major loads. So this table shows the relationship between hardness and tensile strength for steel, brass, and cast iron. So makikita natin na yung brass, yung manipis na blue line ay mas low siya ng number kumpara sa cast iron at steel. So, yung steel may highest number siya for hardness. Tapos, yung cast iron naman, middle part lang siya. So, nandito sa itong nasa pinakataas na numbers, yun yung Rockwell hardness number. Tapos, itong nasa pinakababang part, yun yung Brinell hardness number. So, variability of material properties. So, at this point, it is worthwhile to discuss an issue that sometimes proves troublesome to many engineering students, such as the measured material properties are not exact quantities. Even if we have the most precise measuring apparatus and a highly controlled test procedure, there will always be some scatter or variability in the data that are collected from specimens of the same material. So, for example, consider a number of identical tensile samples that are prepared from a single bar of some metal alloy, which samples are subsequently stress-strain tested in the same apparatus. We would most likely to observe that each resulting stress-strain plot is slightly different from the other. This would lead us to the variety of modulus of elasticity, yield strength, and the tensile strength values. So, ibig sabihin, kahit pa gumamit tayo ng mga apparatus para masukat natin ang material properties ng metal, hindi pa rin sobrang accurate na makukuha nating data. Ibig sabihin, may mga matitira pa, may mga scatter pa rin na measured materials properties. So, ito yung 5 factors na nagli-lead to scatter in measure material properties. First is test method. Siguro ay may hindi naman sa may mali, pero may kulang sa ginawa nating pagtetest. Sunod is variation in specimen fabrication procedure. Sa variation ng specimen para magawa kung anumang test ang dapat gawin. Next is operator bias. Depende sa depende sa operator or depende sa gagawa ng test. Next is apparatus calibration and inhomogeneities and or compositional variations from sample to sample. So, itong limang ito yung mga reasons, possible reasons kung bakit minsan hindi nagiging accurate ang variability ng materials. So, for us to find the typical value and degree of dispersion, gagamit tayo ng computation of average and standard deviation values. So, in this one, an average value is obtained by dividing the sum of all measured values by the number of the measurements taken. In mathematical terms, the average x from some parameters x is x bar is equals to the summation of n and I is equals to 1 multiplied by x sub I over n. Tapos, yung n is the number of the observation or measurements and x sub I is the value of a discrete measurement. So, in order to find the standard deviation S, it is determined using the following expression. Itong equation natin sa left. So, wherein x sub I, x and n were defined earlier. A large value of a standard deviation corresponds to a high degree of scatter. Ibig sabihin, pagtaas ng makuha nating value ng standard deviation, mas malaki yung degree of dispersion natin. So, take a look at this example. The average and standard deviation computation. So, the following tensile strengths were measured for 4 specimen of the same steel alloy. So, sa sample number 1, 2, 3, 4, meron tayong magkakaibang tensile strength. So, yung sa sample number 1, 520, sa sample 2, 512, sa sample 3, 515, at sa sample 4, 522. So, we have to compute the average tensile strength and we have to determine the standard deviation. So, to find the average tensile strength, gagamitin natin yung equation sa naunang slide, which is yung tensile strength bar is equals to yung summation lang ng mga tensile strength over 4. Yung 4 natin, yun yung A. Ibig sabihin ay kung ilan yung samples natin, yun yung magiging value ng N. So, dun sa sa past table, ang sample natin ay 4. So, ang N natin ay 4. So, 520 plus 512 plus 515 plus 522, which is yung tensile strengths natin over N, which is 4, makukuha natin ang value na 517 megapascal. And next, for the standard deviation using the equation 6.22, yung 6.22 natin is yung, we have to find the standard deviation using this formula. So, yung values lang ng tensile strengths natin minus sa nakuha natin na tensile strength, average tensile strength squared. So, ang ating equation ay magiging the quantity of 520 minus 517 squared plus the quantity of 512 minus 517 squared plus the quantity of 515 minus 517 squared plus the quantity of 522 minus 517 squared over 4 minus 1 raised to 1/2, makukuha natin yung standard deviation na 4.6 megapascal. So, in design and safety factors, there will always be uncertainties in characterizing the magnitude of applied loads and their associated stress levels for in-service applications. So, typically, the load calculations are only approximate. So, as the result of our uncertainties in both measured mechanical properties and in-service applied stresses, design or safe stresses are normally utilized for design purposes. For ductile materials, a safe or working stress or SW is dependent on yield strength and factor of safety. So, for us to find the design stress, we will have to use the example design stress is equals to the design factor, which is N prime multiplied by the calculated stress level or calculated stress. So, in safe stress, or working stress, we will use the formula yield stress over the N or the safety factor.